So in this video, I want us to consider this integral log to the power of 4 of the modulus of x. And to calculate it, you would need to use integration by parts 4 times, perhaps 3, depending on what you know of by heart. And generally speaking, in such circumstances, it's better to generate a reduction formula and then use it to calculate the integral. And that's what I'd like you to try to do. So have a go with pen and paper, come back, and there will be a detailed solution and some comments and some additional exercises. See you in a minute. Okay, welcome back. Let's look at what a reduction formula is and then calculate this particular one that we need. So very quickly here, I want to rehearse what a reduction formula is. The idea is that faced with a particular integral, we can generalize the problem to a class of integrals. We call the integrals I, but because they're going to have a label, we can call individual ones I sub n. So for example, in the integral that we're looking at, we might very well call it I sub 4. And then we use the reduction formula to reduce to another integral, and then we use it repeatedly to reduce to an integral that we can do somehow or other. We use integration by parts to generate reduction formulae, so we're going from one integral to the next. And a comment that I've put in red because I think it's important is to avoid errors in doing this, because you're going to have to use the reduction formula more than once. Good presentation and tidying up as you go along helps you to avoid errors. So I'm going to talk about that when I give you the detailed solution on the next slide. So we're looking at this particular integral, and the class of integrals that we're going to look at is the logarithm of x to the power of n, where we're thinking of n as a counting number, a positive integer, or perhaps 0. And this integral we're going to label as I sub n, and that's why I said this integral would be I sub 4. Okay, so let's now generate our reduction formula on the next slide. Okay, here is our class of integrals, I sub n, and log to the power of n of x means log of x all raised to the power of n. So I've just written it this way because it will make life a little bit easier in a moment. It's helpful, I think, to rewrite the integration by parts formula, and to use integration by parts here, the easiest way is to say that this is multiplied by 1, and now we are going to view the 1 as something which has been differentiated, and we're going to integrate it. We're going to get an x, and you might worry that this is going to take us outside the class of integrals, but remember, when you differentiate a power of logarithms, you bring the power in front, so here it would be n. You reduce the power by 1, that's good, we're making the problem somewhat simpler, and we multiply by 1 over x because we're using the chain rule, so we're differentiating the content of the brackets, and that gives us a 1 over x. And in the product, u prime times v, we're going to have this multiplied by this, and you can see already that the x and the 1 over x will cancel, and we're going to stay inside the class of our integral. So now we just substitute this into the integration by parts formula. This is our integral. U is log of x to the power of n. V prime is 1. This is our integral here, in. U times v is log of x to the power of n times x. That's this term. And then we subtract, and then it's the integral of the derivative of u, so that's all of this, which I've written here, and n is a constant. I've taken it outside of the integral. It's a constant that will change when you use it. It can have different values, but it's not a function of x, so we can take it outside of the integral. And then we've got to multiply this by v, and v is x. And we see immediately the good news that the x and the 1 over x will cancel. And now we recognize that this integral is exactly the same as this integral, but we have replaced n by n minus 1. So this we can call the integral, all of this is equal to I sub n minus 1. And let's not forget that it is being multiplied by an n. So this equation here that we've got by using integration by parts once can be rewritten as I sub n, our integral, is equal to this product, these algebraic terms, minus n times I sub n minus 1. So now we have an equation that we can use repeatedly. So if we have I4, our aim is to keep using this equation to reduce it. So we're going to go from I4 to I3. Now we can't integrate I3, so we use it again to get I2. Use it again to get I1. I1 is the integral of log. If you know that off by heart, you could just write it down. Otherwise, you use it again to get to I0. And I0 is the integral of log of x to the naught. So it's the integral of 1. And the integral of 1 is definitely easy. So that's what we're going to do. So on the next slide, we're going to calculate I4 by using this equation repeatedly. And the important thing is to think about presentation and tidying as you go along. So on this slide, I want to calculate I4 using our reduction formula. So I4 is equal to, and now we're going to just rewrite this equation using n equals 4. So it's x times logarithm of x to the power of 4. So it is x log to the power of 4 of x minus 4, because that's what n is equal to, times I3. And now what we're going to do is we're going to use this equation again, but with n equal to 3. So let's try and do this carefully. So we're just going to end up rewriting things repeatedly, but it makes life a lot easier. So this is x log to the power of 4 of x minus 4, and that minus 4 is going to multiply I3. We're going to rewrite I3 as a difference of two terms, so we need to open a big brackets. And now it is x log cubed of x from this term with n equals 3, and then it's going to be minus n is 3 times the integral I, 3 minus 1 is 2. So it's minus 3i2, close brackets. Now, at this stage, what we could do, but we should not do, is we should expand this out again immediately using this equation with n is 2. So you'd have x times log squared x minus 2 times I1. But if you do that, you're going to have nested brackets and minus signs. I think that's dangerous. Instead, what I want you to do is to say that this is going to be equal to, we'll just write it out nicely, x log to the 4th of x minus, and now we're going to multiply the minus 4 into the bracket. So it's minus 4x log cubed x. And now the minus 4 is going to multiply that, and minus minus is plus, 4 3s are 12. So we're going to get plus 12 times I2. Now I could either write I2 here and go on to the next line, or I could, which is what I'm going to do, open a brackets and just write out the equation for I2 immediately. And I2 is given by this with n is equal to 2. So it is x times log squared of x minus 2i1. Now, I1 you might know off by heart, but let's assume that you don't. So we're just going to use this formula again. So we're just going to write x log to the fourth of x minus 4x log cubed of x plus, and now we're going to expand the brackets, so we get 12x log squared of x minus 24, 12 times 2, and now I'm going to open the brackets, and I want to rewrite I1 using this. So I1 is when n is 1, so it's x times log of x to the power of 1, that's just log of x. So it is x log x, and then it's going to be minus 1 times I naught. So that's minus 1, I'm not going to bother to write, it's I naught, close brackets. Now, let's just rewrite this again. Let's just be nice and slow, get it right. Minus 4 log to the fourth of x minus 4x log cubed of x plus 12x log squared x minus 24x log of x plus 24I naught. And now, what is I naught? Well, I naught is the integral of log to the power of naught of x with respect to x, so it's the integral of 1 with respect to x, so it is going to be x plus some integration constant. And now we can just substitute this into here. So therefore, what we obtain is that I4, the integral of log of x to the power of 4 with respect to x, is going to be x log to the fourth of x minus 4x log cubed of x plus 12x log squared of x minus 24x log of x plus, and it's 24 I naught, so it's 24x plus some integration constant. And I'm not bothering to multiply that by 24, I'm just changing its definition really. Let's look at this. This is our answer, and as our answer it's perfectly acceptable. But I would say that it's nicer to rewrite this in the following way. I4 is equal to, if we look at this, this term is multiplied by x, so is this, so is this, so is this, so is this. So let's pull out a factor of x. So we're going to have x, open brackets, log to the fourth of x minus 4 log cubed x plus 12 log squared x minus 24 log of x plus 24, close brackets, plus an integration constant. And that is our answer for the integral, written in a way which is going to make checking it by differentiation easier. So what I would like to do on the next slide is to check our answer by differentiation. And if you haven't done that already, why not have a go first before I show you how to do it? Because it's really nice to see so many terms cancelling. Okay, so have a go on pen and paper and then come back, and you know what you should get. If you differentiate this, you should get log to the power of 4 of x. Everything else should cancel. See you in a minute. Okay, let's have a look at this on the next slide. So on this slide, we're going to check this result by differentiating this. And it's easier having factorised out the x that multiplies everything. We're going to use the product rule and we're going to be able to differentiate easily. If we had x times this minus 4x times this, it would be a little bit more tedious in my opinion. So I think this is a good habit to get into. So let's check it by differentiating, and of course we're going to be using the product rule together with the chain rule. So here we have x times this stuff in brackets. So when we differentiate the x, we get 1 times all of this. So we don't need the brackets around it. We're just going to get this. I've just rewritten the contents of the brackets. And then the next terms we're going to get are going to be plus x times open brackets. And now what we're going to do is differentiate the contents of the brackets. So when we differentiate this is log of x to the power of 4. We're going to bring the 4 in front, like that. We're going to reduce the power by 1, so we go from log to the power of 4 to log to the power of 3 of x. And then what we're going to do is multiply by the derivative of log, and that is going to be a factor of 1 over x. So just to be very careful, let me show you exactly what we're doing. D by dx of log of x to the n, in this case I did it for 4, is n is pulled in front. We have log of x to the n minus 1, and then we multiply by the derivative of log of x, because that is what was in the brackets here, this inner brackets, and that is 1 over x. So that's exactly what we've done here, and you can see immediately the good news that the 1 over x and this x will cancel, and here we've got 4 log cubed x. Oh, here we've got minus 4 log cubed x. They're going to cancel. That's good. Okay, let's just carry on and just do the rest of it. So we've differentiated this term, and now we have to differentiate this term. So what we get is minus, and that's minus 4 times log cubed. So we're going to bring the 3 in front. 3 fours are 12. So we get minus 12. We reduce the power by 1. So we go from log cubed to log squared of x times a 1 over x. And then for the next term that we're going to differentiate, so we're differentiating this term. 12 times 2, when we bring the 2 in front, is going to give us plus 24. And then it's log to the 2 minus 1, log to the 1, that's just log of x times a 1 over x. And then we're going to differentiate this. Minus 24, the derivative of log is just 1 over x. So it's minus 24 times 1 over x. And then we're going to differentiate the plus 24, and of course that's going to give us 0. Close brackets, and if you differentiate the integration constant, you'll get 0 as well. I'm not going to bother writing that. So let's just look at what we have. We need the original integrand. We see the original integrand. Wonderful. What that tells us, and if we didn't have the original integrand, we'd have to think hard about can we get it by combining this, but we have it immediately. That's good. What it tells us is that all the other terms have to add to 0. So let's see exactly how that happens. So first of all, the x out here and the 1 over x is here, 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 and here cancel. So what we've got on this second line is 4 log cubed x minus 12 log squared x plus 24 log x minus 24. Let's see if that cancels what we have above. So the 4 log cubed x cancels with that. The next terms we see are 12 log squared x and minus 12 log squared x. They again cancel. Now, when we're doing multiple cancellations, I think it's quite a good habit to do the crossing out of the terms that cancel in a different way, so that if you start seeing things not working, you can see when you're trying to go backwards which terms you had cancelled with which. Okay, let's now look at the next term. We've got minus 24 log x plus 24 log x, so that and that cancel. And then we have got plus 24 and minus 24, and they again are going to cancel. So everything has cancelled apart from log to the 4th x. So what that tells us is we regain the original integrand. So that tells us that our result for the integral here is correct. Okay, on the next slide, I'd like us to use our result and to work out a definite integral. So let's just pause and we'll have a look at it on the next slide. So to conclude this video, I'd like to use this result to calculate this definite integral from 1 over e to 1 of log to the fourth of x with respect to x, and then use this result that you're going to get to set a bound on the value of e. So have a go and I'll see you in a minute. Okay, welcome back. So the integration constant is irrelevant, it will cancel in the definite integral. You just evaluate this at the upper limit, and at the upper limit you have 1 times all of these logarithms, which are going to all vanish because the log of 1 is 0, but don't forget the 24. So from the upper limit, what we're going to obtain is 24 times 1, so it's going to be 24. From the lower limit, we're going to have a 1 over e from here, and then we're going to get this combination of logarithms, but the logarithm of 1 over e means the logarithm of e to the minus 1, so it's minus 1. Minus 1 to the fourth is 1, minus 1 cubed is minus 1, etc. And again, don't forget the 24 at the end, and don't forget that these logs are multiplied by numbers that are not 1. So if you put all of that together, this is what you will get. The integral from 1 over e to 1 log to the power of 4 of x with respect to x is going to be 24 from the upper limit minus 65. That's what you should get for the contents of this bracket when you put x is equal to 1 over e, but all multiplied by 1 over e, so that's 65 divided by e. Now, what does this tell us about e? If we look at the integral, the integrand is a logarithm to the power of 4, and we're integrating from a smaller number to a larger number, so we're integrating going to the right. This must be positive. So we see that 24 must be greater than 65 over e, as the integrand is positive. So we can rearrange that by multiplying both sides by e, that's positive, so it doesn't change anything, and we can also divide both sides by 24. So it therefore follows that e is greater than 65 divided by 24. So what you can do is you can divide immediately 65 by 8. So that is going to say that we're going to have 3 left on the bottom because 24 is 3 times 8. And 65 divided by 8 is 8 point, and then 65 is 64 plus 1. 64 divided by 8 is 8. 1 over 8 is 0.125. Now we just divide that by 3, and what we're going to get is 2 point, and then we would have 2, 1, which is 7. So 2.7, and then we've got to divide 2.5 by 3, so it's going to be 0, and then we are going to get 25 divided by 3, which is 8, and then we're going to have 1 left, and that's 1 divided by 3 is 333, So we're going to get 3, 3, 3 recurring. And if you remember that E is approximately 2.71828, etc., etc., this is actually quite a nice bound. So I hope you found that interesting. Okay, and with that, I will stop this video.